ready for our second speaker, the one and only Brian Warner. Hopefully you all took this chance to download and install his software so you can follow along the very exciting move things from one computer to another safely. Please give it up for Brian Warner.
Thank you. So I have no jobs to offer, but I do have stickers. So go hit me up afterwards for that. 15 minutes. Okay, how many people here are familiar with Magic Wormhole already? And how many people are not? Okay, you're going to get the 5-minute version of the 45-minute talk of what Magic Wormhole is. That's me. Magic Wormhole is a program that moves a file or a directory from one computer to another safely. You might think this is a solved problem. It's a terrible problem. It really ought to be a solved problem. It should be as easy as Magic Wormhole and as safe as Magic Wormhole. If this were a video, you would see stuff happening, but you didn't. So you run, it's a command line tool, you run wormhole send on one machine, you give it the file name. It gives you out a single-use, randomly generated, pronounceable, transcribable Magic Wormhole code, like 7 Guitarist Revenge, or 4 Purple Sausages, or something like that. On some other machine in the world, you type wormhole receive, and you type in 7 Guitarist Revenge. That is enough for the two sides to find each other, to negotiate a shared session key, encrypt the file, figure out a common pathway to get that ciphertext from one side to another, hash it, send back the hash, confirm everything went through right. If you get nothing else, then remember pip install magic-wormhole. Oh, hey, PowerPoint does this badly. Okay, so it's important to send things correctly. It's important to send the right file to the right place to make sure that you're receiving the right file from the right person. I argue that all of the other tools that you might use to get a file from your computer to your computer are lacking in one or more of these dimensions. The simplest way might be to email something from one person to another, but then you have to transcribe somebody's email address in the opposite direction. Email addresses are not necessarily easy to transcribe. They may have random characters in them because it's a confined namespace. You have to find some unique digits to get something useful, and you're giving that information in the opposite direction to where the file is going to transfer. In addition, all of the servers along the way get to see what the file is. They all get to modify what the file is. It's sitting around in your email server for who knows how long. Somebody might pick it up later after you're done. Similarly, you might put it into Dropbox. Dropbox has a nice little feature where you put something in, you get a URL out, you give the URL to somebody, they paste in, they get it back. Firefox added a thing, send.firefox.com does this inside the browser, has a lot of these encryption features, but you still wind up with the URL that's much too large to easily transcribe to somebody as you're sitting next to them speaking. The real use case for this is two people sitting next to each other at a conference, you have a file, you just want to get it to the computer right next to you. The humans already have this connection, they can already speak to each other, the computers need to be introduced to each other. And that's what Magic Wormhole is about. In the Magic Wormhole case, you speak a short string that is specifically designed to be accurately transcribable from a limited word set in the same direction as what the file is going, and none of the intermediaries have a chance to go and look at the plain text of it. I won't tell you how it works. Actually, I will tell you how it works. There is a baked-in mailbox server that both sides talk to, so that when you type in 4 purple sausages, the 4 really tells that server, I want to talk to somebody else who also types in a 4. And then the purple sausages are the random part that's being used to negotiate the session key. So I'm cheating a little bit because the code can be so short because the host name and the port number of the server is baked into the application on each side. In most of the other cases, you can't assume what application somebody is using, and so you have to have a full URL in there. There's some cool crypto stuff that I won't go into, but if you put the same code into both sides, you get the same random session key out, and it gives you strong security between them. If the codes are different, you get completely random, unrelated session keys. And so it's a nice zero-knowledge property. It means that somebody who's trying to use this, somebody trying to jump in the middle only gets one guess. So the codes can be fairly short. They don't need to have very much entropy because you don't get very many chances to try and attack it. Math. I'm going to skip some slides. Yeah, so the actual data transfer goes over an encrypted pipe. We use that setup phase. We use the rendezvous server, the mailbox server, to do the key exchange and then help the two sides find a more direct connection to each other. There is a relay server that it can use if it can't make a direct connection. So basically, each side says, I'm going to listen on some TCP port. What are my IP addresses? Let me figure those out. And then over the encrypted connection, it says, hey, I think I'm probably listening on this address at this port, this address at this port. How about you try to connect to all of those and see what happens? And the other side does the same thing. They try to talk to each other, If any of those connect successfully and passes a handshake that's based on the session key they negotiated earlier, great, they have a direct TCP connection. They can send the rest of the ciphertext over that. If that fails, they both talk to this relay server, and that just kind of glues the two TCP connections to each other. So there's an encrypted transit thing in which it's a kind of custom protocol that is encrypting all the records as it goes over that pipe. There's a library API. I'm working on some stuff. Right, so that was the 45-minute presentation. Now, what I want to tell you about in the remaining 10 minutes. What I've been working on the last year or so is a new protocol for this. I'm trying really hard to get as many geeky science fiction references into the API as possible. So the image here is that you start with a little narrow beam wormhole. Like you have these two wizards and they're on hilltops and they speak out these magic codes and somebody goes, 4 purple sausages, and this wormhole pops open. And then you can send stuff through it because on the other side of the world, there's some other wizard that said 4 purple sausages and a little wormhole popped open. The dilation protocol is like, I've been watching a lot of Deep Space Nine recently. And so it's like, great, you do your other magic spell and the wormhole like grows and now it's big enough that you can throw files into it and they pop out the other side. So Magic Wormhole has these two protocols. There's the mailbox protocol, which is about doing the key negotiation and doing a setup. And then there's the transit protocol, which is about the bulk data transfer. The mailbox protocol has an API that looks basically like this. You generate, this is the Python API. It's all based on twisted. When I say yield there, that's a deferred coming back. You kind of wait for something to happen. So you generate a code that needs to talk to the server. It needs to allocate some stuff. So that's why it's an async thing. You say what the code is, then you can send messages. And these are like arbitrary binary blobs that you can send to the other side. You can get back a message. And the downside of this protocol is that all the messages go through this server. So it increases the latency. You two may be right next to each other, but all the messages that are in this protocol have to go off to my server and back again. It's limited in size, frequency, and quantity because I don't want to have that much data running through my server. So this is really for the setup phase of something. But what we use it for in the file transfer protocol is to send these hints to the other side. So we say, hey, I'd like to send you a file. Is that okay? It's going to be this size. It's going to be this name. And here's all the ways you might try and connect to me. And then the response is going to come back saying, yeah, that's okay. Here's all the ways you might try to connect to me. And then the phase after this is where they actually try to make that connection. In Magic Wormhole right now, that is done with a special object called transit, which is it's a separate file altogether, a separate Python module. And you construct one of these transit sender objects and you give it the encryption key. Everything it does is going to be based off of that negotiated session key. You ask it to enumerate the IP addresses and to listen on a port, and it gives you back a set of hints. And then it's the other protocol's job to somehow get those hints to the far side. It gets back the corresponding set of hints from the other side, and it plugs them into this transit object with that add their hints line. And then it says, okay, try to connect, and then send as much data as you can. And every time you do an f.read or an f.write on this socket here, it is going, or a send record rather, that's going to get encrypted. It's going to get sent over this connection. So the benefits of this is that it's usually a direct pipe. If you're sitting right next to each other, if your machines can see each other, then they're going to make a direct TCP connection. That's going to be super fast, super low latency. There are no limits imposed by my server. It's not costing me anything for these two machines to talk to each other directly. And this also implements, if you're familiar with Twisted, the iProducer and consumer interfaces are how flow control is managed. So in fact, that loop there wouldn't be great for your memory consumption if you're sending a 4 GB file, because it's basically going to read everything in from disk, and it's all going to pile up in the kernel buffer. And it's just going to like fill all of your memory, and then eventually some of it makes it out the network socket. So what you really want to do is pause that and not read something from disk until you've got an okay from the far side that you can go ahead and open up the window and send some more. So the real version of this, you can connect one of these transit objects into a producer-consumer thing. Anyway, that's the old stuff. The new thing that I'm working on, these dilated wormholes. So the API for this is going to be based on twisted endpoints. So you take the wormhole and then you say dilate, and you get back a triple of endpoint objects. And if you're familiar with the way that endpoints work in Twisted, this is the kind of standard way that you take any sort of client-like protocol and you plug it into a transport, or any kind of server-like protocol that wants to listen for inbound connections. So you wind up with 3 kinds of endpoints that you can plug anything else into. The nice thing about endpoints is that you can make more of them. You can make multiple connections for a given endpoint. So all of these endpoints, all of these connections are getting multiplexed through the same TCP pipe. The crypto for this is using a protocol called Noise, which is being used in WhatsApp for the encrypted messaging stuff. It's getting used in the WireGuard VPN software. It's written by the same folks that did Signal. So much pretty respected cryptographic engineering going into that. The outbound endpoint, it's an endpoint like the usual TCP, the usual twisted endpoints are like TCP v4 or Unix domain socket or something else like that. So you take that outbound endpoint and you can connect to it as many times as you want. You get as many connections as you want going to the far side. On the remote side, that inbound endpoint is a regular listening endpoint. It's a stream server endpoint in the twisted world. So you can post some sort of listening factory on that. It'll get as many connections as is ever made to it. So the nice thing is that when you're doing your file transfer stuff, you can then use one new transport, one new connection for each file you're sending. And you've got two of them going in opposite directions. So it means that both sides can initiate a connection to the opposite side, regardless of who initiated the wormhole. In addition, there's this control channel, which opens up automatically, and it looks like a client on each side. What I found in setting up the file transfer stuff is that it's not always obvious who's on first. And you might have two clients that are talking to each other, and there's no clear, like, I'm going to send the file, you're going to receive the file, or I'm the client and you're the server. A lot of times it's really pretty egalitarian, and you've got two machines that are just introduced to each other, and then they have to decide who's going to do what. So the control channel is a way where both sides do the same thing, and then they both do a connect on it. It looks like a client socket from both sides. And then they can start sending messages, and then after that they can figure out, right, I'm going to choose a random number, you choose one, whoever has the higher number, right, I'll be Alice in this protocol, you'll be Bob in this protocol. So that turns out to be useful from the application point of view on this. Other interesting thing about this is that these connections can be durable. So when you start this up and the two sides say, I'm listening at this address, I'm listening at this one, let's connect, maybe they establish a connection, maybe you start sending some really large file, and then you go and close your laptop because you're going home for the day, and you get back home and you want to open up your laptop again. When you bring your laptop back online, it's going to have a different IP address because now you're on an entirely different network. We still have that connection to the rendezvous server, to that mailbox server. So one side can say, hey, you're back. I haven't heard anything from you for a while. I timed out. I dropped that connection. Where are you now? Do you want to try this again? And this side can say, oh, now my IP address is blah, blah, blah. How about we try to connect to that? They reestablished a new connection there. They were keeping track of how much data got acknowledged, which data has not. So from the point of view of the endpoints, this data stream never went down. Those endpoints never close until you close the wormhole manually. You do w.wormhole.close instead of one of these endpoints.close. So you get these durable connections that survive motion from one network to another. This means that file transfers just will pick up automatically where they left off after moving from one network to another, which is a big frustration with the way that Magic Wormhole works right now. If you have a long transfer and it dies in the middle, you're kind of out of luck. You have to start over again from the beginning. This also enables bidirectional initiation of transfers. So my goal here is to have a GUI application where you type in the wormhole code and you wind up with an application that has a little picture of a wormhole, of course, and you drag files into it, and the file icon kind of goes and gets stretched out in wormhole like something in Deep Space Nine, and then it pops out the other side and falls into your downloads folder. But you can do the same thing on this side and have something pop out on this side. So the fact that each of these programs can independently, spontaneously initiate a connection to the opposite side through that shared wormhole object makes the UI of the application much nicer. You don't have to declare up front whether you're going to be sending or receiving. You don't even have to declare that you're going to be doing anything right now. You can just start the application, do the code thing, have that connection, and then leave it there running for days, and then decide, all right, now's the time I want to drop the file over. So it's going to enable a lot more application friendliness from there. So you might be saying, hey, this sounds great. When do I get to use it? Let me tell you about my 3 rules of project planning. This is stuff gleaned from decades of experience. You might want to write this down. Number 1, Brian's first rule of project planning. Do not ask me about project planning because I'm crap at trying to figure out schedules and how long stuff is going to take. I've been working on this for probably about 9 months or so, and it's about 80% complete. And as you all know, that's the other 80% that's going to take most of the time. So we're making good progress on it. Rule number 2 of how to make sure a project gets done on time: don't go and start a company while you're trying to get something done. It's a lot of fun, but let me tell you, it consumes all of your time. And rule number 3 is don't go and try and port it to Rust when you're halfway through this. It's fun. You should go check it out. We're making some really good progress on this. But it consumes a lot of time from kind of what the core mission is. The reason that the Rust port of this is interesting is because we decided to go with a sans IO kind of core to it. Great document there. I think Brett Cannon wrote that. This is a model where you're building a network protocol without any actual networking. You're going to have some kind of object that knows what the protocol messages are. It has the state machines that know how you respond to an inbound message and how you go back, what you send out in response to that. But there's no socket calls, there's no IO, there's no read and write calls inside that piece. And you write a different piece that talks to that core and actually speaks to the network. And the nice part is that that makes that core much easier to test. And in this case, the Rust implementation, Rust is an interesting language. It's really difficult to have object graphs that have cycles. In fact, it's really difficult to have an object graph that's not a tree, because any one object kind of wants to be owned by exactly one other object. So in the Python version, we have a bunch of state machines, but they all have pointers to each other. And when you tell one of them to change state, it may like emit 2 other messages that kind of kick off. It's like, you know, a little mousetrap firing thing bouncing all over the place. In the Rust version, we just couldn't do that. And you have to have like a single owner object that has all the state machines as its direct children. So instead, we do this kind of cross-machine event queue, where each one of these little state machines, you tell it to change some state, and it makes the change, and it returns to you a list of events that it wants this boss object to distribute out to the other events, to the other machines. That turns out to be super convenient for testing, because every one of these state machines has exactly one input that always returns one type of output, one list of events. And you can just like run that in a unit test without worrying about mocking out anything else. It's turned out to be really, really handy for that. And I'm thinking about backporting that to the Python form because it makes the testing so much better. And our main goal with this Rust thing, apart from kind of being interesting and the interesting distraction, is that it's probably going to make it easier to do bindings in other languages. So there are folks that want to use this from Go, there are folks that want to use it from Node.js, and rather than trying to port this same logic to all of those different languages, we can compile this into a dynamic library and then write bindings to that in all of these other languages. A lot of that binding stuff is automated, and you have to write IO glue for each of these different languages, but that's going to be very different in those languages anyway. So we're aiming it for helping in the embedding and the binding story. So that's it. Please go pip install Magic Wormhole, come grab the sticker, and I'll be around for questions. Thank you.
You want to take some questions?
Yeah, if you got any.
Nick?
So I know it's only like 9 months old, so it's probably a little early, but has any, well, I don't know how many people are working on this, or if any like third parties have like checked it out, like tried to audit sort of the security of it or the protocol?
I've not heard of anybody auditing. I would love to find people to go and do that. There is a company in Berlin called Least Authority Enterprises that does a lot of work on Tahoe, which is another project that I was involved in, and they are using Magic Wormhole for distribution of Tahoe that helps you connect a storage client to a storage grid. So they have a couple of people that are working on this kind of process. Related to that, I put together a tool to let you do a Git checkout over a protocol that we use in Tahoe called Foolscap, which is kind of a encrypted objects, remote object invocation sort of a tool. And that gives you Git clone and then a big long random string that has all of the kind of encryption keys and hashes and stuff in it. I recently added Magic Wormhole into that. So you can say Git foolscap publish or invite, and it gives you out a wormhole code. And then somewhere else you can say Git foolscap clone and type in the wormhole code, and that glues those two together and gives you a Git checkout that's securely going just to that machine. So those are the applications that I know of that people are using this for. I think the least authority people may be able to find some money and some people to do audits of stuff like that. And then the Rust port, we've got 2 guys from India that have been hacking on it along with me. And Alex Gaynor has been involved as well. So it's slow, still kind of small, but getting some momentum. Yeah.
So I've only ever used this as a client, but
yeah.
if I wanted to like self-host the mail server,
mm-hmm.
is that I haven't checked out the source yet. When
To-
to install, so I'm just kind of curious. Is that in documentation as well?
Yeah. So there's on PyPI, there's Magic Wormhole, there's Magic Wormhole Mailbox Server, there's Magic Wormhole Transit Relay, and you can install that. It is less useful if you're making an application that kind of embeds this for something, which I think is great, and I'm encouraging people to use Magic Wormhole as a provisioning tool. Then yeah, run your own mailbox server, bake that into your application. Both sides know about it. It's not as useful to run a different mailbox server to use with the default file transfer tool, because you'd have to add in a command line argument on both sides to go and do that, and you lose a lot of the benefits of the small code. But yeah, it's easy to run that. It's just a twisted plugin service. So it's like twist Wormhole mailbox server, and then that launches it.
Thank you.
Yeah, there, yeah, in the back.
Okay. Have you ever thought, so did I understand correctly that it's only one-to-one? There's no one-to-many?
Correct, yeah, the
Have you ever thought of,
encryption.
like taking the encryption that you have, taking a BitTorrent tracker, extending that so you can get the one-to-many, and then fan out?
Yeah, a couple people asked for that. The particular encryption key agreement mechanism being used here, PAKE,
That would have to be-
is not easy to do with a one-to-many. And part of it is that the security comes from the fact that you only get one guess at it. So if you want to say two different people could go and get it, you probably need to add a bit to the code to make it safe enough to use twice. And then kind of keep increasing the code length depending on how many people have to go and use it. Yeah.
I have the same question.
Okay. Yeah, there's an issue on the GitHub tracker, GitHub / with some more information on it.
So you run the Rendezvous server, right? I use Magic Wormhole probably at least a couple days a week.
Mm-hmm.
I'm kind of curious now that like it's getting a little more popular. So you got some stars. Like, what's traffic on that?
It's
central
getting,
server like?
I think somebody uses it about once every 30 seconds right now. And I think, so the relay server, like, if two machines can't make a direct connection to each other, they have to go through the relay server that I run. That is using, I want to say like 300 gigabytes a month or so. And so, I'm running that on a Linode instance. I've probably got 3 or maybe 6 terabytes a month kind of coverage for that. So I think I've got at least another 6 months before that starts getting into the place where it might cost me more actual money.
At that point, you can get a sponsorship.
Yeah, I do that. Or I'm thinking there's a hosting provider called Scaleway that thinks that their network is so good that they don't charge you for, like, they don't cap your bandwidth. The servers are in Paris or Netherlands or something, so latency wouldn't be that great. But for the bulk transfer phase, that's probably not a big deal.
Yeah.
So I think I might end up moving the transit relay off to their machines. Yeah.
What proportion, do you have a stat on like what proportion get a direct connection?
I do not. Yeah, I don't get that much information about what's going on there because everything's encrypted. I could look at the number of successful connections, and so when the clients finish, they report back to say whether they were happy or whether they were sad. Yeah. And I could compare the number of those to the number of connections going through. I think I have the information for that, but I don't know it off the top of my head. Yeah.
I guess to that point, is there a good way to troubleshoot why it's not going peer-to-peer? Like, I've used it at my work with a coworker, and I get really slow.
The peer-to-peer thing is really lazy right now, and I really could use some help figuring out NAT hole punching. And so basically right now it runs ifconfig to get all of your local IP addresses, which is not the best tool for that anyway. And then it gives that whole list to the far side, and it tries to connect to all of them. And like whichever one succeeds first wins. And if none of them wins within a couple seconds, then it goes to the relay. So that's going to fail if the IP addresses on if you're behind a NAT, it's wrong. It could be doing UPnP. Like, it would help us if we could do UPnP and ask the router, please give me an external address that would work for this. It would help if we use a fixed local port and we ran everything over UDP, so that a lot of routers will just like automatically pull that back in. It would help if we asked the mailbox server, hey, what IP address do I seem to be coming from? Compare that to what I have locally and go, yeah, I'm probably behind a NAT. This is not going to be that useful. So there are a bunch of techniques that have been around for 10 years, but I don't know how to implement them, that I think we should glue in there. And I'm told that if you do that stuff, then about 80% of household connections can probably make a direct connection.
Is that all on the GitHub issue?
Yes, it is.
Okay, great.
Yeah.
So why not using Q2Q there?
Does it really exist? Does it? I mean,
last time I heard from Griff, like it's anyway like optimistic, right? Worst case, it fails and you fallback.
Yeah, there are other tools out there to kind of do this stuff. I haven't dug into them enough. Like my prediction of how likely they are to help multiplied by how much effort it'll take has not yet reached that threshold. And also see previous comment about starting a company and porting stuff to Rust. So,
Tell us about your new company if you can.
it's called Agoric. We're trying to do safer programming languages for hostile execution environments. We just got some seed funding last week.
Wow, congrats.
That's about it.
Great.
Yeah.
Yeah, so you mentioned the person next to you in a conference use case, right? So if I like, I don't know, like an IRC client or something, and I PM someone else, with like, I guess eavesdropper is just the people who are like listening in an IRC or
it's a race between from the time that you say the code, like you tell the person next to you. We've done this at PyCon a couple of times. It's like, hey, give me that test case. It's like, well, let me wormhole to you. Okay, 4 purple stars. And so it's this race between the time you say that or it's a race between the time the attacker manages to type that in and the legitimate person manages to type that in. Sure. And the nice thing about using Pake for this is that once the legitimate person has typed it in, that code is no longer secret. You can broadcast it and it doesn't matter anymore. It's a fairly narrow window for that. Is there one more? Yeah.
Right now, the only transfer servers that you are hosting it.
That's
possible to become decentralized.
Yeah. The transit relay is easier to work with because it's something that can be negotiated. So in fact, both sides say, I'd like to use relay X, I'd like to use relay Y, and they try both of those as they go through. At the moment, they only ever advertise the same one that I run. But you can run your own and add it to the list of stuff that gets advertised. And so it can be decentralized, and we have more options for that than we do for that mailbox server. But at the moment, you have to like add environment variable, add a configuration option in order to enable non-default.
Very good questions.
All right, cool. I'll be around later on if you want to ask me some more. And come and grab a sticker afterwards.